Now, I know all of you already have a decent background in electromagnetism. You also know many of the things we might learn in the first few lectures, right? Definition of voltages, currents, and so on. We'll still go through it quickly just to make sure everything is in place, right? Before we move on to the really new things you're going to learn as part of this course. So the first thing we need to define are these electrical quantities of interest, right? The fundamental electrical quantities that we plan to use in electrical engineering actually, but as far as this course is concerned. So we'll try to draw an analogy. So let us say we take, what is the other force? The electromagnetic force is probably, maybe the first or second most important force in the universe. What is the other one? The other common one is the gravitational force. So we'll try to draw an analogy to that. Of course, there are two other forces which we will not consider, right? Because it's a little bit more exotic. But let us just take the example of a gravitational field. Okay. So let us say there exists some gravitational field. Okay, and I'll take the surface of the Earth as reference. And let us say there is a point mass, okay, m, which exists in this field, right? And you know that the existence of this mass at a certain height h above the surface, so I'll call this h1, okay, gives it a certain amount of potential energy, right? And let us say this mass moves from, takes some path and moves to a new location. So this is 1, this is location 2 at a different height. So let's say that second height was h2 above the surface of the Earth. Okay, you know that the mass, there is a difference in potential energy, okay, between the two locations. What is the difference in potential energy? Okay, this is the difference in potential energy, okay, that the mass has experienced when moving from location 1 to 2. Similarly, if you take the same example of an electric field in which you have a point charge Q, okay, and let's say there is an electric field and it moves from one location to another. So let us say this was location 1, it moves to a second location through some path. Okay, there is a difference in potential energy experienced by this charge. Okay, what is that difference in potential energy experienced by this charge? Can you quantify it? That is related to something called the potential difference, right? That is related to something called the potential difference. So remember, the potential difference is the original definition. In electrical engineering, we tend to call it the voltage, right? We tend to call it the voltage. In EE terminology, this would be called the voltage. Okay, so you can define the potential energy, the difference in potential energy for this charge also. What does that depend on? It depends on the initial location. In most cases, it depends on the initial location and the final location, right? It might take any path, but in most cases, it would depend on the initial location and the final location. Similarly, if you take the example of the gravitational potential energy, you have a mass, okay, it starts from height h1, it may go higher, it may go lower and so on, but the difference between the initial point and the final point, the initial height and the final height, okay, will give you the difference in the potential energy between the two states. Similarly, barring a few specific instances which we will try to briefly look at towards the end of this class, you will find that if you take a point charge in an electric field, okay, you go from point 1 to 2, okay, so the difference in potential energy depends on the initial location and the final location only, okay. So it goes from point 1 which has a voltage V1 to point 2 which has a voltage V2, okay. What is the difference in, okay, so this thing is is represented in terms of the potential difference, what is the actual delta E? What is the actual delta E? So it's Q into V1 minus V2. Okay, just like you had a representation in terms of the height, now you have a representation in terms of the potential. Okay, so that tells you what this, you're already aware of all of this, I assume. How many of you are not aware of this kind of existence of something called a potential and the energy being related to the potential? I assume you've already seen this several times, right? Okay, so this of course depends only on the initial and the final, barring a few specific cases. Okay, so now if you see what you have studied so far in physics, you would have represented the quantities of interest would be the electric field and the charge, right? Q and E are the most important quantities of interest, right? You are interested in Q and E. Okay, obviously they are more basic in some form, right? However, we can't go back to the charge and the electric field every time we want to analyze the behavior of specific systems. Okay, there are easier quantities under which can be used under certain conditions. So our job is to learn what these easier quantities to use, I mean what these are, okay, and when we can use them and what are the conditions under which these will be violated. Normally if you take a case in physics, you might have a certain spatial distribution of charge, you might have a you might have an electric field which may be constant, may be varying. You specify it in terms of those cases. But really in electrical engineering you have more specific scenarios where you do not necessarily need to worry about a specific spatial distribution of charge. Okay, you are more interested in the movement of charge in a certain way, okay, and how it can be described. So in electrical engineering, okay, we will replace these two quantities with something which can be directly related to them. So of course E, we have seen the electric field can be directly related to the voltage. What is the other quantity that can be related to the charge? You would have heard of something called current, which is normally represented by the letter I. Okay, what is the relationship between I and charge? It's a rate of flow of charge. Okay, so this is nothing but the rate of flow of charge. So what we'll do is, in a majority of cases in EE, we will not, be looking at the charge, we will not be looking at the electric field. We are more interested in the voltages and currents because they are more tangible. Okay, in reality you will have to go back if you want to. These are easy to use, easy to analyze, easy to manipulate. Okay, however, you will have to go back to the physics of the system if you need to do more specific things. For example, if you want to measure the current or voltage, you will have to go back to the electric field, you will have to go back to the charge and so on. And obviously there are certain cases where you cannot always separate this dependence. When we come to learning what kinds of electrical elements are present, we'll learn a little bit more, but you already know the existence of certain elements called capacitors and inductors, right? So you know that a capacitor, for example, the charge across a capacitor is an integral quantity describing the capacitor. Similarly, for an inductor, the magnetic field is an integral part of what an inductor is all about. However, when you place these electrical elements called inductors and capacitors inside an electrical system, you can still relate the charges and the magnetic fields to usable quantities, namely the voltages and currents. And you already know about these relationships, right? I assume JE now includes questions on, inductors, capacitors, and so on, right? So you already know all of this. This is just an introductory class. Okay. So we are going to be interested in the voltages and currents in a majority of cases, and we are going to be dealing with these for a long time to come. What about these two guys? In the EE courses that you will encounter, you will come across these quantities also. You will learn more about the physics of the system in definitely two courses, and I'll tell you what those are. Okay, you will definitely encounter these in two courses. Okay, one of them is electromagnetic fields, which you can kind of think of as a follow-up course to physics 2. Okay, and the other course is called solid state devices. Okay, so in these two courses you will be looking further. I mean, in these two courses you will be interested in the charge, in the magnetic field, in the electric field, and so on, right? In these more physical quantities. But if you see the other courses, right, obviously EMC, okay, analog circuits, digital circuit design, okay, machines, power systems, and so on, you will definitely be interested in voltages and currents. So now let's look at some of these electrical elements that we'll be encountering. First of all, what is an electrical element? So let us say this is some unknown element. Okay, I've just shown it as as some rectangle. This is an unknown two-terminal element. So this is called a terminal. Okay, these are the terminals. This is a two-terminal. Okay, you can also have three-terminal elements. I'll just show it as a bigger black box. So this has terminal 1 and 2. This has 1, 2, and 3. Okay, you can also have three-terminal elements, four-terminal elements, and so on, right? Of course, you already know examples of these simple two-terminal elements. For this two-terminal element, okay, you can describe it using these two quantities, voltage and current, that we have just been studying. Okay, remember that the voltage is the potential difference between 2 points. Okay, it is and the current is the rate of flow of charge. Okay, if I take a two-terminal element, I have a current I in flowing here. I have a current I out flowing out the other way. Now, there are certain assumptions we make when we talk about these kinds of voltages and currents in electrical engineering. We will assume that there is no accumulation of charge inside the system. What does this mean for us? If we say there is no accumulation of charge, okay, the current going into the system has to be equal to the current coming out of the system, right? Obviously charge is conserved and there is no accumulation of charge. So the current going in has to be equal to the current coming out. Okay, so we'll just call this current I. Okay, and based on these movement of charges, there is also going to be based on a certain potential difference, there is going to be a movement of charges. Okay, and that is represented by the current I. And for any general two-terminal element, there will be an inherent relationship between the current through the element and the voltage across the element. it can be represented in either form. Okay, the current as a function of the voltage or the voltage as a function of the current. This may be a linear relationship, this may be a non-linear relationship. At this point we don't know. Okay, in fact there are elements with both kinds of relationships. What if I have a 3-terminal element? Okay, so let us say I have a current I1, I have a current I2, and I have a current I3 in the directions shown. Okay, what can you tell me about these currents? You know charge is conserved. Okay, you know there is going to be no accumulation of charge inside this 3-terminal element. So what does that mean for us? I3 should be equal to I1 plus I2. Okay, in general for any n-terminal element, okay, what you will find is the sum of current flowing into the system has to be equal to the sum of current leaving the system, so that there is no charge accumulated inside the system. Similarly, between these terminals 1, 2 and 3, I can define a set of potential differences, electrical potential differences. Let us say this was V1 and V2, and I can also describe a potential difference between these, which is V3. Remember, just as in the case of the gravitational case, the potential energy, it needs a reference. I defined that as the surface of the earth. It is not an absolute quantity. Similarly, voltages are defined between two particular terminals. Okay? You can't arbitrarily say that the voltage of a terminal is something. It needs to be with respect to something else. That's why it's a potential difference. Okay? What can you tell me about the potential difference, all these voltages V1, V2 and V3? Again, you know that the potential difference is related only between the two terminals of concern. Okay? If there is a potential difference V1 between terminal 1 and 3, V2 between 2 and 3, okay, you can directly come up with a relationship for the potential difference between 1 and 2 in terms of these two voltages V1 and V2. Right? What is the relationship here? V1 minus V2. Correct? I have assumed a certain direction for the current. I have assumed a certain sign for the voltage. You could assume the opposite sign also. Okay? You make a certain assumption and proceed with that. If I had assumed that V3 was in this direction, okay, if I had defined V3 to be the difference between 2 and 1 instead of 1 and 2, the signs would have changed. So this is a very common mistake, okay, which people do in tutorials, exams and so on. So just be very careful. You follow a certain fixed terminology, you will not go wrong.
So,
yes?
why should IN should be IN is equal to I1 for all tests if the response is different in...
Okay, we are not considering those cases. You are right. We are not considering cases, we are considering cases, okay. We will consider that, I'll explain towards the end of class. When we consider the cases where this conservation of charge and accumulation of charge is violated, okay, little bit later. Let me just go through this and I'll explain the cases when it is not violated. Okay, maybe I'll just give you a quick idea of what I mean. So if I take let us say I take a element, okay. I say there is a current I entering and a current I leaving. What do I mean? So first of all, there is some charge entering here at a certain rate, okay, and there is a certain charge leaving at the same rate outside, okay, away from the element. I also assume that this flow is instantaneous from one terminal to another. Okay, I am assuming that there is an instantaneous flow of charge. Okay, obviously if this flow of charge is not instantaneous, the relationship between these two terminals would be broken. Correct? For example, if the rate of charge going in was, okay, I'll give you a simple example. Let us say you take a really long wire, right? You take a really long wire and there is some current flowing in here. You know that there is the charge cannot flow from one end of the wire to the other end of the wire instantaneously, because there is a certain limit to this speed at which charge can flow. What is that limit? It is the speed of light, right? So the speed at which the charge flows always has to be less than or equal to the speed of light. In many media it will be much significantly lower. So what really matters is the length of the wire and the size of the system and the rate at which these quantities, electrical quantities, are changing. Okay? In the systems that we will encounter in this course, we will assume that this charge travels instantaneously. Okay? Does that answer your question? Okay. Okay? So these particular relationships have a specific name. I think you already know what these laws are called. What are they called? They are called Kirchhoff's laws. Okay, so these are systematized as very specific laws which are pretty much used all over electrical engineering. So they are called Kirchhoff's voltage law and Kirchhoff's current law, okay, often abbreviated as KVL and KCL. Okay. Now, to learn it in a very formal way, we need to understand, with respect to electrical systems, we need to learn a couple of more things which you probably already know. You need to know what an electrical circuit is. What is an electrical circuit? An electrical circuit can be defined as an interconnection of two or more electrical elements. Okay? Okay, it is an interconnection of two or more elements. So I'll take the simplest example. This by itself, I can call it an electrical circuit, but it's kind of a redundant electrical circuit. Okay? Because why is it a redundant circuit? Any idea why I'm calling it redundant? Obviously, since this terminal is not connected to anything else, right? I know that based on the conservation of charge and accumulation of charge, current coming in has to be equal to current going out. So there is no current through either of these two elements. Okay? So now I need to complete what is called a loop. Okay, this is a loop. Okay, so in other words, a loop is formed in an electrical circuit when it starts from a particular terminal. Okay, and in fact I'll call this a node. Okay, a node is an interconnection of, is the intermediate point, the point of connection between two elements is a node. Okay, it's a point of connection of between two terminals of different elements, right? and a loop is formed when I start from a particular node in the circuit and I am able to traverse through the circuit and arrive back at the same node. Okay, so I traverse through the circuit. So I start from this node, let us say, I go through multiple elements and I am able to arrive back at the same point. That is what is defined as a loop, as an electrical loop. Start from a node, traverse through any element or several elements, okay, and arrive back at so in the initial circuit that I drew, when I did not have this connection, that did not have a loop. It had one node but no loops. This particular, once I have made this connection with an ideal wire, how many nodes does it have? It has two nodes, okay, and one loop. And obviously there are, depending on the number of elements that you draw, you can think of many different connections. Right? You can take 4 elements and make one loop, make two loops, make three loops, and so on. Okay? And you could also add further elements, for example. How many loops does this circuit have? 3 loops, right? So I have loop 1 here, loop 2 here, and loop 3 here. Okay? So now that we know what a node is and what a loop is, we can now come to the formal definition of Kirchhoff's laws. Okay? Now Kirchhoff's voltage law says when you go around a loop, okay, the sum of the voltages the sum of the voltages around the loop is 0. And that has to be the case, right? You start from a particular node, okay, you're going through several elements and you're arriving back at the same point, right? You know that the potential of that particular point with respect to some reference is not changing when you arrive back. So you start from that point, you arrive back at the same point, you are at the same potential. So what that means is all the sum of all the potential differences that you went through when traversing through the loop, through multiple elements, that has to be 0. Right? Any questions? Okay. What about the other law, Kirchhoff's current law? What does that tell you? This is again a restatement of what we mentioned earlier. So based on the principle of conservation of charge, okay, and assuming no local accumulation of charge, we said with respect to an element, we said it enters through terminal 1, it leaves through terminal 2. We can apply the same thing to a node. So I'll take an example. So let us say, okay, I take 3 elements connected together at one node. Okay, I have a current I1, I have a current I2, I have a current I3. I can apply this principle of conservation of charge at this node. Okay, what will that tell you? So if I apply that for this specific case, I1 has to be equal to the sum of I2 and I3. The rate of flow of charge flowing into the node has to be equal to the sum of that leaving the node, right? So I1 has to be equal to I2 plus I3. in a more formal way, this is just an example, in a more formal way, I can say the sum of all currents entering a node this has to be 0. Okay, the sum of all currents entering a node has to be equal to 0. In other words, what are the currents entering this particular node N1? Based on my definition, from element 1, okay, I'll call these elements 1, 2 and 3. Okay, from element 1 you have a current I1 entering that particular node N1. Okay, from element 2 you have a current of minus I2 entering that node. From element 3 I have a current of minus I3 entering that node. So if I had to at N1, so I1 plus minus I2 plus minus I3 is 0, and this is exactly a restatement of the same principle. Okay, so this is Kirchhoff's current law. Let us say I take a particular electrical circuit, okay, and let us say it has n nodes. Okay, a corollary of Kirchhoff's current law is that for a system with n nodes, you can only define n minus 1 independent currents, right? If you have a system with n nodes, you can only define n minus 1 independent currents. Okay, or if I have an element with n terminals, okay, I have several terminals, n terminals. As far as the element is concerned, I know charge is not accumulated. Again, I can only have n minus 1 independent currents, right? The last one is directly related to the other n minus 1 currents. Is that clear? What about the voltages? Let us say I have n loops or m loops. Okay, for each one of these loops I can write Kirchhoff's voltage laws. Okay, obviously when I have n nodes, the potential difference between these nodes will also be related in a certain way when I go through these loops, right? And same thing for this n terminal electrical element. If I define V1, let us say I define V1 with respect to these two, V2 with respect to these two, and so on. I take, there will only be a certain number of independent voltages and currents that you can define. Okay, and Kirchhoff's voltage laws and current laws will define how many independent voltages and currents that you can define for a particular electrical circuit or for a particular electrical element with a certain number of terminals. Any questions? Okay, very good. Now let us take a quick example of some of these two terminal elements that you might be aware of. Okay, what are the simplest two terminal elements that you are aware of? So let's take an example of a resistor. You already know about this. This is a symbol of a resistor. Okay, I can define a certain voltage across it. I can define a certain current through this resistor. What is the relationship between these two? I can define it as V equal to IR based on Ohm's law. Okay. Sorry. I can define it in terms of this equation also, where G is 1 by R. What is G? Okay. This R is the resistance. Okay. The symbol of which is ohm. This is the conductance, which is 1 by R. The unit of this is Siemens. Okay. I can also draw the voltage to current relationship on a set of axes. What will this look like for a resistor? It will be a straight line passing through the origin. Okay. Okay. So what is the slope of this? The slope is G, which is 1 by R. Okay, I have taken the y-axis as I and the x-axis as Z. Okay. Any other two-terminal element that you know of? Okay. This is what is called a capacitor. Okay. It's defined by its capacitance C. What is the relationship between the voltage and the current? What is the relationship between the voltage and the current for a capacitor? Come on, people. I equals C dV by dt, right? And there's a class going on here. Okay, stop talking or move away from the building and talk. Okay, so you also know the existence of an inductor. So this is defined by its inductance L. Okay, so again I have a potential difference V, okay, and a current I. What is the relationship between V and I for an inductor? V equals L di by dt. Okay, so now a few things, okay, related to these equations which we write. So first of all, you can take any reference direction for the currents and voltages. Okay, I think it should be pretty obvious that if I take an element, okay, which has a voltage V and a current I, okay, this is exactly the same, okay, as taking the voltage in the reverse way and defining the voltage to be minus V and assuming a current of minus I to be flowing in the opposite direction. Okay, that should be obvious. Okay, number two, the current, you may already know this, but the current is defined as the flow of positive charges. Even though in a real circuit it may be electrons that may be flowing, okay, you assume as far as positive current is defined as that is the direction of flow of positive charge. Okay, so that is the definition as far as we are concerned. Okay, what happens inside the particular element or at the atomic level does not really matter for this kind of analysis. Okay, so you can define these kinds of relationships. Any other two terminal elements? Okay, We will consider the easier cases, which is a battery or a voltage source. Okay. The symbol for a voltage source is this, is a circle with the polarity defined across it. Okay, so let us say I take a battery of a specific voltage V0. I take a voltage source with a specific voltage V0 and it has some current I flowing through it. Actually, how do you define a voltage source? An ideal voltage source? How is it defined? What is it? No current flows through it. Anything else? Anybody else? How do you define an ideal voltage source or an ideal battery? Somebody raise their hand so that I can ask you to repeat what you're saying. What's your name? Kevin. Okay, Kevin, tell me, how do you define an ideal voltage source? This you probably know from before, I would assume. Voltage is constant independent of the current, right? An ideal voltage source can support any current through it while maintaining the same potential difference, okay, a very specific potential difference across it. Okay, so if I take a voltage source of value V0, it is defined by this value V0, okay, it can support any current through it. Okay. Okay, potential difference across terminals is V0 independent of or regardless of the current. Okay, so if you had to draw the IV characteristic of this, particular voltage source, what would that look like? This would be, okay, a straight line intersecting the x-axis at V0, right? This would be the IV characteristic of an ideal voltage source. Similarly, you can define what is called an ideal current source. Okay, as shown the current direction upwards, it could be downwards also. Remember, the reference direction does not matter. If this source is going to force a current to flow from terminal 2 to terminal 1, a current I0, you can also take it as a current source forcing a current flowing from terminal 1 to 2 of minus I0 inside the element. Okay, remember the direction of current is just a reference direction. Okay, just remember that. And let us say it has some voltage V across the terminals. What is the definition of an ideal current source? Current is constant. So current through the element will be constant irrespective of the voltage across its terminals. Okay. So independent of V. So if you had to draw the IV characteristics for this, okay, what would that look like? This would be parallel to the x-axis with an intercept on the y-axis of value I0, right? So you can draw the IV characteristics for any, any of these elements. Now, actually one other point, when you go back to the, when you look at the inductor, right? You might have studied in physics that the voltage is minus L di by dt and not plus L di by dt. So that matters in which way you take the reference voltages and currents. Okay, this is just a symbol. Okay, this twisted thing here is just a symbol, okay, representing the inductor. Okay, so we are defining this inductor, these terminals, such that a current I flows through it, a voltage V is developed across it. Is that okay? If you really take a piece of wire, run a current through it, create a loop, and want to measure its inductance, then you will need to worry about the signs, right? There's a certain rate of change of current. You can figure out what the voltage developed across the terminals is, and then you will have to worry about the signs. Is that clear? As far as we are concerned, this is just a symbol representing this with a certain voltage across the terminals and a certain current through it. Is that okay? Okay, so we'll stop here. In tomorrow's class, we'll continue with these two terminal elements further. I think somebody mentioned a diode. We will probably not be dealing with it immediately. Later on in the course, we'll try to quickly look at what a diode is. We won't be looking at that now for a very specific reason, which we'll look at next class.